Now I would like to demonstrate the solution to exercise 4. In this exercise, we will fit multivariate nonlinear regression models to the dataset with volumes of 6 brain tissues to predict age at scan. We will evaluate them and check for the bias error. We will compare 3 models: linear ridge regression, polynomial ridge regression, and kernel ridge regression with Gaussian kernel. We will start with linear ridge regression, and you already know how to tune and fit linear ridge regression because you've done it in the previous notebook. Important thing is that we have feature matrix X and target vector Y where the dataset has been loaded. So please make sure that you run all the cells in this notebook up to the exercise to make sure this dataset is available, and also that all the libraries and functions are available. So the code has been already prepared for us because we've done an exercise like this already. And if we run it, we can see that the best alpha was 0.1 and the cross-validated root mean square error was 1.27 weeks. And the model was saved in this variable model lin. But what we want to do now, we want to check for the bias in this linear model. And for that, we will make a function plot targets. And this function will plot expected versus predicted target values. So the problem with this data set is that we really cannot plot it because we have 6-dimensional feature space, but we can still plot the expected and predicted target values and see whether they match. So the function is already here, but it's not complete. So we need to complete some information in it. So first we need to calculate the predicted target values. So a model and the data set come as parameter, as the arguments of this function, so we can use them. Model.predict. So we assume that the model is fitted already, and we predict it from the feature matrix, of course. And then we need to plot, and it says plot expected targets on x-axis. So expected targets, that's y. And predicted targets on the y-axis. So that will be y-pred. Okay, so this is it. So now we call this function using a model lin that we tuned before, and of course our data set as well. The code is already here, so we just run it. And here we see the result. So if the model was fitting perfectly, all the samples would appear on this red line, which is x equal y, or actually expected target values equals predicted target values. And we see that for all the ages is nicely centered around this line, but not for younger ages. So for the babies between 25 and 30 weeks, the model predicts higher age than in reality. So we have a bias here. So the answer to this question is yes, there is a positive bias for younger babies. So positive meaning that their predicted ages are higher than the ages that they really have. Okay. So let's now look at the polynomial ridge regression. So first we need to tune the model for this data set. So model is already created here. It's a pipeline of 3 objects. First 2 are transformer objects. So first we create polynomial features, then we scale them to the standard values, and then we run ridge regression. So we have the parameter grid as well, so we will check polynomial ranges from 1 to 4 only. This is to make it faster. And also we have a range of alphas here. Okay, so let's do the grid search. So we use object grid search CV, and we need to input the model, the parameters, and a number of folds. Then we need to fit the grid search CV. So grid search.fit xy, that's our data set. And the code to remember this, the model that we fit is already here. It will be in variable model poly. So let's see whether this works. And it worked fine. So now we have model poly. We can print out the best parameters and calculate the performance. So the code for that is here. So we already have code to print the polynomial degree, but we have to write it to print out alpha. So model poly. And remember, model poly is a pipeline. So first, before we can print out the parameter, we need to reach the object. So we do that using name steps. And then the name that we gave to that object. And for alpha, we need to reach the reach object. So we call it reach. And now this is our reach regression, so we can just access alpha like this. So here we calculate root mean square error using cross-validation, and here it's a model poly that we fitted and the data set. So let's do it. So we see that the best performance was for a polynomial of second degree, and the alpha was 1. And the cross-validated root mean square error is 0.84 weeks. So is it better than linear ridge? Of course it is. We had, with linear model, we had 1.27 weeks. So this is a clear improvement. So we are happy. So clearly this bias is showing. So let's now plot the result as well. So I answer, yes, we improved from 1.27 weeks to 0.84 weeks. That's my answer. And let me plot so that I know whether the bias has disappeared. So plot targets. Now I need to put my model. It was model poly, right? It's here, and X and Y. Okay, let's see. And we see that we reduced the bias significantly if we compare to this plot, right? Great. So is there less bias than for the linear model? Yes, clearly. Okay, the final task is to tune the kernel ridge with Gaussian kernel. So here we have to fill in more code than before. So first we define the model, that's kernel ridge. And we also have to say which kernel we want. So it will be kernel equals RBF. RBF stands for a radial basis function, and it is in reality Gaussian kernel. Okay, the parameter grid is here, so we have to check different alphas and gammas. So grid search CV, we input the model, the parameter grid, and number of folds. Then we fit it, not fit, XY. And this time we have to ourselves write remembering. So grid search dot best estimator underscore. Okay, let's run the search. Okay, that ran fine. And now we need to fill in the code to evaluate the performance and find the parameters. So best gamma. So we don't have a pipeline now. This is simple kernel rich. So this is much easier to do. It's model kernel dot gamma, and here model kernel dot alpha. And root mean square error model kernel xy. And let's see. So we see that best gamma was 0.003, best alpha was very small, and we get average cross-validated root mean square error 0.77. So is it better than polynomial ridge? Yes, of course it is, because we had 0.94. So this is our best performance. Okay. So, final thing for this exercise is to plot the expected versus predicted targets. Plot targets. And now model kernel X and Y. And you see that there is almost no bias left. So it's even better than the polynomial model. Answer: there is no visible bias error. It seems better than polynomial model. Okay. That's it.